In this video, we're going to talk about maximizing or minimizing a function. We're going to run through 5 problems, and those problems are written out on the first page of the notes if you are following along with the notes. We're going to find 2 non-negative numbers that sum to 50 and whose product is maximized. So generally what we're doing in this section is we're trying to maximize or minimize some quantity, like maximize a product or minimize a cost, for example, given some restriction. So every problem will have a restriction between our different variables. In this case, we have a restriction that we want our numbers to sum to 50. So first thing that we'll do is we'll just introduce some variables. What we're trying to find in this problem here is 2 non-negative numbers. So let's say something like let x be the first number and let y be the second number. And that way we have names for our 2 numbers and we can start to do some algebra and write down some equations. So I would say that's basically step 0 of the problem. And then for step 1, we're going to write down 2 things. We're going to write down what we're trying to maximize or minimize. So in this case, we're trying to maximize a product. And we're also going to write down the restriction on our variables that was stated in the problem. So we're told that we want the 2 numbers to sum to 50. That's going to be our restriction. So x plus y equals 50. And we're told that we want the product to be maximized. Okay, so we're trying to maximize x times y, the product of our 2 numbers. And the quantity that we're trying to maximize or minimize, we're usually going to call that f, just so we have a short way to refer to that. So we're going to maximize f equal xy with the restriction x plus y equals 50. So what's important here is just to be able to tell apart the quantity that you're trying to maximize versus the restriction. So the restriction will be an equation that has a constant in it. It will say something like x plus y equals 50. Whereas the quantity that you're trying to maximize, it's really just an expression. It's x times y, and we're just saying we're calling it f. So that is step 1 done. And in step 2, what we're going to do is use our restriction to get f in terms of one variable. Because the idea is that in a minute, we're going to need to take the derivative of this function f here. And right now that function involves 2 different variables. So taking the derivative is not going to be very much fun, but we can use our restriction to turn f just into an equation involving x, or a function involving x, and then life will be much easier when we take our derivative. So here's how this is going to work. We're going to start with our restriction, which is x plus y equal 50. And we're just going to solve for one of the variables. Often we'll solve for y. So we'll say, okay, y equals 50 minus x. And then what we can do is take that, put that into our function. So instead of calling our function xy, see, now we can call our function f equals x times 50 minus x. And that way we've got a single variable function. So in a moment, we're going to be taking the derivative. Therefore, we can decide if we want to leave f in the form that we've written it here, or we can decide maybe it'll be a little easier if we just expand it out. I'd say it's easy enough to expand, so why don't we just call it 50x minus x squared and make life a little easier for ourselves. So this is our best version of f that we've encountered so far. So that represents the product of the 2 numbers, but it's written in a friendly form. And in step 3, what we're going to do is set f prime equal to 0. So let's think about what we're really trying to accomplish here. We are trying to maximize our function f. So in the language of our previous video where we did curve sketching, what we're trying to do is we're trying to find a relative maximum for this function. And we saw in our curve sketching discussion that the way you do that is you find your critical points. So you set f prime equal to 0, and then those will lead you to any relative maximum or relative minimum points that our function has. So once you've got your function in terms of a single variable, let's find f prime and set it equal to 0. Okay, so just looking at this highlighted version here, let's calculate f prime. It's 50 minus 2x, and we want to set that equal to 0. So 50 minus 2x equals 0. can solve that little equation that says 50 equals 2x. In other words, x equals 25. Okay, and then from there, step 4 is just to answer the question. So we'll call that answer. And that's a good time to scroll back to the question and just figure out what it's actually asking for. So let's scroll back up. We want to find two non-negative numbers that sum to 50 and whose product is maximized. Okay, so we found one of the numbers. We know x equal 25 is one of the numbers. And then we can use our restriction here to figure out the second number. So if we know x equals 25, we can plug that into our restriction, x plus y equals 50, because the restriction is the equation that tells us how the two variables are related. So if we figured out what x is, we can figure out what y is using the restriction. Okay, so 25 plus y equals 50. In other words, y is also equal to 25. And then if you want, you can summarize with a sentence or just a little phrase at the end to show that you have interpreted the question correctly. So you could say something like, the two numbers are 25 and 25. So out of all the pairs of numbers that add up to 50, all the pairs of non-negative numbers, you could think about 1 and 49, 2 and 48, etc. If you start taking products of these, 25 and 25 is the pair that's going to have the biggest product out of all the possible pairs of numbers. So that's the problem that we've just solved. So let's take a quick glance back over the different steps, and we're going to apply these to 4 other more physically relevant problems. So our steps were really step 0, if you want to think about it, is introducing your variables, because without that you don't even have the language to do the other steps. In step 1, you write down what you're trying to maximize and what your restriction is. In step 2, you use your restriction to get your function in terms of one variable. And then in step 3, find critical points by setting f prime equal to 0. And in step 4, just answer the question. So just as an aside here, as a follow-up to the question that we just did, we found one critical point in the previous problem. That was where x equaled 25. But you may have a lingering question about that. The question would be, how do we know that point was a relative maximum? So how do we know it was a relative maximum as opposed to a relative minimum, or as opposed to a critical point that is neither a relative maximum or relative minimum? Well, there's a quick way to know that for sure if you are concerned about that. And this method is called the second derivative test. I consider this to be optional, but it may be reassuring to you in some problems. You might like to use it as an optional tool just to check that you've done your work correctly. I won't specifically test you on it. So I'll just remind you of some of the quantities that we had in the problem. We found f prime was 50 minus 2x. And when we set that equal to 0, we found that our critical point, was at x equal 25. Okay, so here's how the second derivative test works. At the end of the problem, once you think you found your answer, you can take the second derivative. So you would have already had the first derivative calculated in the problem. So take the second derivative. In this case, it's -2. And in general, what you're supposed to do is plug in the value of your critical point. So we found x to be 25, so we would plug that in. Now, in this particular problem, f double prime is constant. So no matter what x value you plug in, you're going to get -2. But that's not always the case. So sometimes your f double prime will involve an x. In that case, you're plugging in whatever your critical point is that you found. Okay, now all we really care about here is the sign of f double prime at your critical point. The important thing to notice here is that it's negative. So let's think back to curve sketching and think about what that tells us. Second derivative being negative tells us that our curve is concave down. So concave down, that's a situation where the cereal is on the floor. And then you can see by drawing that picture that if your curve is concave down, then that means for sure you have a relative maximum. If we had found that our curve was concave up, then we could conclude that we've got a relative minimum. So here's our second problem. We're going to cut the corners from a 15 by 15 centimeter metal sheet to form an open-topped box. Okay, let's draw a picture of this and make sure we understand what's going on. So we got this square metal sheet, and we're going to cut corners out of it. So we are actually cutting square corners out of it. All the corners are going to have the same square dimensions. So you can imagine if this little square here gets cut out and that little square gets cut out, what that's going to leave us with is a flap like this that can be folded up to form the side of the box. So that will fold up to form the side. And similarly, if we cut out all four corners, you can imagine this part here is a flap, that part there is a flap. So these are forming the four sides when they get folded up. And then this blue dotted line here, or this blue dotted square, will be the base of the box. So it's an open top box. It's not going to have a lid on it. And what we want to do is find the height of the box that maximizes its volume. So find the height of the box that maximizes the volume of the box. And we also want to figure out what is the maximum volume. All right, so let's say step 0 here is to introduce some variables. So I'm going to draw a bigger version of this box. Okay, so one dimension that we need for sure, or one variable that we need for sure, is this x value representing the side length of the square that's being cut out. Now, if this is x, if x is that length from there to there, then this is also x, this is also x, this is also x. So all these squares have to have the same side length so that when you fold up the flap, the sides meet nicely to form just the edge of the top of the box. Okay, so all of these will be x. I'm not going to label them all, but just from physical intuition, we should understand that they're all going to be the same x value. Okay, then the other thing that we know is that the metal sheet itself has dimensions 15 centimeters by 15 centimeters. So what you could do is you could say, well, I need a name for this length here that runs basically along the flap, knowing that this total side length here is 15. And let's think about this y. So we could call it y. More naturally though, 15 minus 2x, because the idea is that if you call it y, then automatically you know y plus 2x equals 15, and you know that at some point later in the problem we're going to be solving for y, and we would figure out y equals 15 minus 2x. So I say we might as well do that part now since we know it's coming. So we know that our dimension of our little square that's being cut out, x by x, and we know the length of our flap. You could call it y, but as we've said, we're going to call it 15 minus 2x just to get a bit further ahead in the problem. Okay, so that's step 0 done. Step 1, so we have to write down what we're trying to maximize or minimize. In this case, we're trying to maximize volume. And we also want to write down a restriction that relates our variables. Okay, so the restriction we actually don't have to worry about because that was just the restriction that y plus 2x equals 15, and we've already built that into our diagram, so don't need to worry about that. Let's just concentrate on what we're trying to maximize. So we're trying to maximize the volume of the box. Okay, and whatever you're trying to maximize or minimize, you're going to give it the name f so that a little bit later on we can take derivatives of that quantity. Volume of our box is going to be the length times the width times the height, but let's think about what that looks like in terms of x. Okay, so I think I'll draw another version of the box just over on the side here. So it's going to have a square base, and the dimensions of the base are going to be 15 minus 2x by 15 minus 2x. And then it's got this little side that folds up, that's formed by the flaps there, folding up. And so the height of the box is going to be that x coming from the corner that's folding up. Okay, so instead of saying length times width times height here. Let's say 15 minus 2x squared to just represent the area of the base, and then times another x to represent the height. And that's the quantity that we're trying to maximize. Essentially, step 2 is already done here. Remember, step 2 was to turn our function into a single variable using our restriction. Yet we decided to do that right away in the diagram. So that's done. And that means we're jumping into step 3. So we need to set f prime equal to 0. And that's going to lead us to our critical points, which will lead us to any relative maximum or minimum points that this function has. Here's where we get into the calculus. So we've got our function highlighted up at the top of the screen here, and we're going to focus on finding f prime. Now it's up to you whether you would like to use the product rule and the chain rule here, or whether you would find it easier to just expand f out. I think they're both valid ways to go. So let's say here, I'm just going to expand out. I think that's easy enough to do. So let's expand the square. We'd have 225 minus 60x plus 4x squared. That's still getting multiplied by x. So if we multiply through 225x minus 60x squared plus 4x cubed is our function f. And so I'll highlight this version. So let's calculate f prime. It looks like 225 minus 120x plus 12x squared. And we're going to set that equal to 0. Okay, so this is a nice time to try out our quadratic formula. So x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And it looks like we're going to get a couple different x values, and then we'll just investigate those. So changing the sign of the x coefficient, we get 120, and then we're going to go plus or minus the square root of, I'm going to take a negative 120 squared minus 4 times 225 times 12, that's all under the root, and then divided by 2 times our x squared coefficient. So just a caution here with the quadratic formula, the a refers to whatever the x squared coefficient is. Normally that's written at the front, but because it's written at the back here, just because of the way f was written, we just need to be a little careful about that. So it's 24 that we are dividing by. Okay, so let's check out our roots here. So if you go to the calculator, this stuff under the square root works out to 60. So our different x values then, we have 180 over 24 as one of our options, and the other option is 60 over 24. Okay, so let's just turn that into decimals. So x equals either 7.5 or 2.5. So let's take a look back at our sketch, and it will turn out that only one of these numbers is reasonable from a physical point of view. So let's look back at our sketch. So I've just decluttered this a bit so that we have room to think about this. So imagine what would happen if x were actually 7.5. If x were 7.5, that would be equivalent to cutting out all of this metal sheet. Everything would be a corner, basically, and you would have nothing left for the base. So that would lead us to 0 volume for the box. And surely that cannot be our maximum volume. That actually turns out to be our minimum volume. So just based on physical intuition, we could say, no, that doesn't make sense. And the correct answer is going to be when we choose 2.5 as the side length of that little corner that's being cut out. So a little bit of physical intuition there helps us decide between our two answers. So this one here leads to the relative maximum for the volume, and this one here leads to the relative minimum for the volume. Okay, so we're going to stick with x equal 2.5, and from there we can answer the question. So let's scroll back to the question and just figure out what it's asking for. It's asking for two things. It says find the height of the box that maximizes the volume. Okay, so that height is x. And we also want to give the maximum volume as well. Maximum volume, we'll get that by plugging into our volume formula here. So step 4, here's our answer. So the height is what we're calling x. 2.5 centimeters was what we figured out there. And the volume, that came from the formula f that we were trying to maximize. It was 15 minus 2x all squared times x. And we're just going to plug our x value of 2.5 into this to get our maximum volume. So plugging in, we'd have 15 minus 5 all squared times another 2.5. So that's going to be 250 cubic centimeters. So that's the biggest the volume can get if we make the best choice of corner size to cut out. So we are omitting problem 3 just because I don't think it's that relevant from a physical point of view. So we got 3 more problems to go. Let's do example 4 here. So we're going to find the point on the line y equal 2x plus 3 that is closest to the point 2, 1. Okay, let's draw a picture. Let's say this is our line, y equal 2x plus 3. I don't think I really need coordinate axes on here to draw this picture, but this is a line with a positive slope. And then we've got some point 2, 1 that's not on this line. So let's say our point 2, 1 is here. The way you know for sure that's not on the line is when you sub in y equal 1 and x equal 2. It doesn't satisfy that equation. And we want to find the point on the line that is closest to our point 2, 1. So if we just think about our picture here, we move in a direction that's perpendicular to our line, figure out where that intersects our line. This is going to be our point that we're interested in. So in step 0, what you're trying to do is introduce some variables that you can work with through the problem. Why don't we call our point here x, y? So I'll just write this in words. Call the point x, y. And that way we've introduced our variables x, y. So step 1, we need to write down what we're trying to maximize or minimize, and we also need to write down our restriction. Okay, so let's talk about the restriction first, because I think that's the easier of the two processes. So the restriction is that the point that we're looking for lies on the line y equal 2x plus 3. So that means our variables are related by the fact that y equals 2x plus 3. Okay, then in terms of what we're trying to maximize or minimize, we want this point xy to be as close as possible to the point 2, 1. So if we think of our distance here, let's call this d, distance between the 2 points, we are trying to minimize that distance. Okay, so minimize our distance d. So let's zoom in on this drawing here and let's see if we can find a formula for this distance d that we're trying to minimize. Okay, so really what we need to talk about is just these 2 points. One is xy and the other one is 2, 1. And what we need is to find a formula for this distance d here. So you may remember from one of your previous math courses having done something similar. The way to figure out the distance is just to realize that we've got this right triangle here. So we can think about the vertical distance between our 2 points, and we can think about the horizontal distance between our 2 points. Those two side lengths are at right angles, so then we could use the Pythagorean theorem to get our distance d. Okay, so let's start with the vertical distance. So that comes down to the y values. One of the coordinates is y, and the other one is 1. So if we just subtract those two coordinates, if we go, say, 1 minus y, that's going to give us our vertical distance here. In fact, it doesn't really matter if you say 1 minus y or y minus 1, because in a moment we're going to be squaring the side lengths. So I'm not going to stress too much about which one we're subtracting from which one. So for the horizontal distance, if we do that in the same way, it would be 2 minus x is how far we're traveling in the x direction between those 2 points. Again, if you said x minus 2, that's totally fine because in a moment this is going to be squared anyway. So then from the Pythagorean theorem, d is just going to be the square root of the side lengths squared and then summed up. Okay, so I'm going to write this formula up here in step 1. So we're going to be minimizing d equal the square root of 1 minus y all squared plus 2 minus x all squared. And this part here is just the visual to go with figuring out that formula d. Now, if we look ahead in the problem, we know that we're going to need to be taking the derivative of this function here, this d. And the fact that that has a square root in that is going to make the algebra a little complicated. So there is an equivalent way to proceed, a way that might make life a little bit easier. So it is actually equivalent to minimize d squared. So let's think about this. D and d squared are clearly different numbers. You know, if our minimum distance comes out to 4, for example, then d squared would be 16. So d and d squared are not the same number. But when we say minimize d, that is actually the same process as minimizing d squared. Because when we say minimize d, we mean find the point that makes d as small as possible. And that is the same point that makes d squared as small as possible. So when we say equivalent, it's equivalent to minimize d squared, what we're saying is that this gives the same answer, the same point, xy, as minimizing d. So we are actually going to minimize d squared, and since this is the function that we're going to be working with, let's call it f. It's going to be 1 minus y all squared plus 2 minus x all squared. Okay, and then I'll write down our restriction as well. The restriction was that y is going to equal 2x plus 3. So this is where we are at the end of step 1. So now step 2, we want to turn this into a single variable problem. So the idea is that you use the restriction, which is that y equal 2x plus 3. You put that into your function so that you can turn your function into something that just involves x and that doesn't involve y anymore. So our function is 1 minus y all squared plus 2 minus x all squared, and we're just going to sub in here and replace the y with the 2x plus 3. So this first term then looks like 1 minus bracket 2x plus 3 all squared plus 2 minus x all squared. Okay, so let's work on cleaning up this first term. If we just look inside the brackets, we'd have a minus 2, we're just looking inside the brackets here. We'd have a minus 2x, and we'd have a 1 minus a 3. So that would be a negative 2. So if I rewrite that first term then, we could say f equals minus 2x minus 2 all squared is really what we've got there, plus 2 minus x all squared. Okay, so that now takes us into a single variable function. That means now we can think about taking f prime, setting it equal to 0, and getting our answer. So just like in the previous problem, you could choose to expand that out if you feel more comfortable with that, or we could practice our chain rule. So I think in this problem, I'm going to go with not expanding it out, and we're going to do some chain rule when we take this derivative. So this was our function from the end of step 2, and now step 3, we are going to take f prime and set it equal to 0. So that's where we find critical points for this function. And that's going to lead us to any relative maximum or relative minimum points. So first thing we should do is actually take f prime. So let's try our chain rule. So you can see the chain rule is going to come into play because you've got an inside function raised to some power, and same thing happens in the second term. So the power will come down in front, inside function will stay the same, power will decrease to a 1, which I'm not going to write down, and then we'll multiply by the derivative of the inside function, which is negative 2. And then we're going to go plus and do the same thing for the second term. So the 2 comes down in front, inside function stays the same, power decreases to 1, and then we multiply by the derivative of the inside function, which is -1. Okay, so let's clean this up a little bit because we are going to be setting it equal to 0. So you could multiply the 2 and the -2 together just to give you a -4 out front. So we could think about cleaning that part up. And then here you could multiply the 2 and the -1 to have a -2 there. So let's start to expand this out. This would be 8x plus 8 minus 4 plus 2x. So in other words, 10x plus 4. Okay, and we want to set this equal to 0. So 10x plus 4 equal to 0 tells us x equals -0.4. So very last thing we need to do here is just answer the question. And for that, I would scroll back to the original problem and just figure out what the question is asking for. So it just says, find the point on that line that is closest to the point 2, 1. So in other words, we need to find the x and the y coordinate of our point. Okay, well, by the end of step 3, we've already found our x coordinate. So to give our answer, we would say, well, our x coordinate is -0.4. Our y coordinate, well, we'll need to think about our restriction that relates x and y together. So we know that y is equal to 2x plus 3. And if we actually sub the x equal -0.4 into this, so take that, put in here, then y equals 2.2. So then you can say the point is -0.4, 2.2. Now, the question didn't ask for the minimum distance, but just as a side note, just in case you're curious. So the minimum distance is, if we wanted the minimum distance, we would need to go back to the formula for d, which was the square root of 1 minus y squared plus 2 minus x all squared. So if you sub in your coordinates, your -0.4 and your 2.2 into this, you can check that the distance comes out to about 2.7 units. So not asked for, it's just really in case you are curious about what that minimum distance is. So I think the biggest takeaway from this problem, something that was pretty unique here, was this idea that we decided to minimize d squared. So I'll just scroll to that relevant part here. We decided it's equivalent to minimize d squared. Making d squared as small as possible forces d to be as small as possible. A closed rectangular box has a square base. So closed meaning it has a lid as well. If the base is square, I'm just going to say the base is x by x, and then it's got some height to it as well that it's probably different than x. So let's say our height is h, just introducing some variables as we go. The material for the top and the sides of the box costs $1 per square centimeter, whereas the base is more expensive. The material for the base costs $2 per square centimeter. We want to find the dimensions that maximize the volume of the box if the total cost must be $144. Okay, so we got our two variables, x and h, written out there. First step is to write down what you're trying to maximize or minimize. In this case, we're trying to maximize volume, which would be x squared h. Okay, often we'll call the thing that we're trying to maximize f, just so that we've got a name for that function. And then we need a restriction. So the restriction is what's going to be a little bit of work here just to get this figured out. The restriction is going to come from the cost. So we know that the total cost must be $144. Okay, so think about units here. So we want to be measuring everything in dollars. So on the left side, we're measuring in dollars. On the right side, we're going to have a bunch of terms here that are added together. And those terms are going to look like dollars per square centimeter times a certain number of square centimeters, which is going to get us back to dollars. So for example, let's think about the base of the box first. Okay, so how much does the base cost? It's $2 per square centimeter times how many square centimeters is the base? X squared. So that's what we're going to do for the base. Now let's do the top. Okay, so the top costs $1 per square centimeter, and how much area does it cover? X squared. Okay, now let's think about the sides. First of all, there are 4 sides. So I'm going to put a 4 out here, and then we can think about each of the sides. So the material for the side costs $1 per square centimeter. Okay, and how many square centimeters is on each side? It would be, just looking at our diagram here, X times H. So that way we have calculated in dollars how much this box is actually going to cost. Okay, so let's do a cleaned up version of this. New and improved version of our restriction, 3x squared plus 4xh equals 144. So I'm going to put all this stuff in a box and just highlight, the cleaned up equation that we really care about. So that is step 0, which was introducing our variables, and then step 1, write down what you're trying to maximize or minimize. You can call that F, and then write down a nice restriction relating your 2 variables. So step 2, we now want to turn this into a single variable function. And so what you do is you start with the restriction and you just solve for one of the variables. Okay, now it would be much easier to solve for h here because h only occurs once in that restriction. So let's start with 3x squared plus 4xh equals 144, and let's solve for h. So 4xh is 144 minus 3x squared. In other words, h is 144 minus 3x squared over 4x. And what we're going to do is take that and put that into our function. Okay, so let's scroll back up. Our function was, we can see it at the top of the screen, it's x squared h. So that means our function can now be written as x squared times h. So 144 minus 3x squared all over 4x. Okay, so we've basically just taken our h here, we've multiplied it by x squared. When you multiply a fraction by something, multiplying this fraction by something, it's equivalent to just multiplying the numerator of the fraction by that thing. So that's how we get f equals, basically this is our h times x squared. Now the nice thing here is that a factor of x is going to cancel. So let's show that factor canceling. And we could even clean f up just a little bit more because we know there's going to be a derivative coming in our next step. So we basically got this 4 on the bottom. Okay, I'm going to think of that as a 1/4 that's sitting out in front. So that's our 4 from the denominator. And then you can just multiply the x through. So you can say it's 144x minus 3x cubed. So just to go over that one more time, you could say 144x minus 3x cubed all over 4. That's fine. Or you can take that all over 4 and just write it as a 1/4 that's sitting out in front. And because I know that we're going to be doing a derivative, I'm just thinking having the constant sitting out in front might make life just slightly easier when we do our derivative. So we've used our restriction here to get f just in terms of x. We did that here, and then we decided let's just clean f up just a little bit more so we can do our derivative. So with that, we're ready to find critical points. So step 3 is to set f prime equal to 0, and that will find any relative maximum or relative minimum points. Okay, so let's calculate f prime. We're just looking over here at our function f. So calculating f prime, the 1/4 would stay in front, and then taking the derivative inside the brackets, 144 minus 9x squared. And what we'd like to do is set this equal to 0, and that's going to lead us to our answer. So to solve this equation here, let's start by multiplying both sides by 4. That will just clear the fraction. And then once you get down to an equation like this that has two terms, might as well bring your terms to either side of the equation. So that works well anytime you've got two terms. 144 can be divided by 9. That works out pretty nicely. So that gives us x squared equals 16, and that means x could be either plus or minus 4. Well, since x represents the side length of the base of this box, we can just disregard the solution x equal negative 4, and we figured out, okay, that means x equals 4 centimeters. So now let's scroll back to the question and just figure out exactly which quantities we're supposed to give in our answer. So we're given all this information about the box and how much the material costs. The last sentence is usually where it's asking you what you're trying to find. So find the dimensions that maximize the volume if the total cost must be such and such. So basically we want to give the 3 dimensions in our answer. And from looking at our diagram here, the 3 dimensions are x, x, and h. So we know x, we figured out that it's 4 centimeters. Therefore, we just need to know a little formula for h, and we can scroll back through our work to figure out where we last saw a formula for h. Oh, here it was. We said h was 144 minus 3x squared over 4x. So that's what we'll use to answer the question. So answer, let's find h, which is 144 minus 3x squared over 4x. So we're going to put our solution x equal 4 into this, and let's figure out what h comes out to. So that comes out to 96 over 16, which is 6, and that's going to be in centimeters. So to actually answer the question, you could say the dimensions are, well, the base is 4 centimeters by 4 centimeters, and then the height is 6 centimeters. So 4 centimeters by 4 centimeters by 6 centimeters gives us the maximum volume of the box that we can build if we've just got $144 to work with. So last problem for this video, we're told that a cylinder has volume 100 cubic centimeters. What dimensions minimize its surface area? Okay, well, before going into this problem, we should make sure that we know the formula for the volume of the cylinder and also the surface area of the cylinder. So let's think about both of those. I'm just going to draw a picture of a cylinder here to help us with this reasoning. So let's think about volume first. If you wanted the volume of the cylinder, you'd think about what is the area of a circle, and then you would just multiply that by whatever the height of our cylinder is. So we'll actually put some variables on here. Let's say r is the radius of the circle and h is the height. Okay, so volume for the cylinder, we'll take the area of the circle, pi r squared, and multiply it by the height to get that volume. Now, for the surface area of the cylinder, imagine this cylinder were something like a can of soup. So you could imagine peeling off the label of the can of soup. And if you unfold that label, what it's going to give you is a rectangle. So imagine just peeling off that label, unfolding it, laying that piece of paper flat. That's going to be a rectangle. So the dimensions of that rectangle, you would have h from the height. And if you actually unfolded your label and you're thinking, how long is this rectangle going to be? Well, it's actually going to be as long as the circumference of that circle. So it'd be 2 pi r. So if we think about that label then, that label has area 2 pi r times h. But that's just for the side of the cylinder. The cylinder also has a top and a bottom. So the surface area from the top would be pi r squared, would be the area of the top circle, and then you'd have another pi r squared for the bottom. So let's just call that 2 pi r squared. Okay, and then we can draw a little or write a little note for ourselves and say that's from the side, and that part there is from the top and the bottom. And this is probably a good time to say it's good to be familiar with the different geometry formulas that we've seen in the video. So I would not expect you to kind of invent geometry formulas out of thin air. But now that we've seen the formula for the volume of the cylinder and we've seen the formula for surface area of the cylinder, then I would expect you to be able to use those on a test because you've seen them in the lecture videos. So basically, the problems from this section will be similar to the problems that you've seen in the lecture videos. So let's think about where we're at. We've introduced our variables, R and H. So that's step 0 of the problem. We also figured out some of these handy formulas that we're going to use in the problem. So I think we're ready to get into step 1, which is to write down what we're trying to maximize or minimize, as well as our restriction. So the question is, what dimensions minimize the surface area? Okay, so we want to minimize a function f, which represents surface area, which we know is 2 pi RH plus 2 pi r squared. So we want to make that as small as possible. And let's figure out our restriction. So we're told in the question that our cylinder has a volume of 100 cubic centimeters. Okay, so that's going to be our restriction. Volume is pi r squared h, and we want that to be 100. So step 2, we're going to try to turn this into a single variable problem. Right now, our function f has 2 variables in it, r and h. If you think about it, the r appears a couple of different times in this formula, whereas the h only appears once. So basically what you want to do is you want to get the h out of this. It's the one that occurs least often. So let's think about getting the h out of this, and then we'll just come up with a nicer formula for f that we can take the derivative of. So start with your restriction, which is pi r squared h equal 100, and let's solve for h. So h equals 100 over pi r squared, and we're going to sub that into our function f so that we can get the h out of there. So I'll just write down what f looks like. It's 2 pi rh plus 2 pi r squared, and let's replace that h here. Replace this guy. So we get f equals 2 pi r times 100 over pi r squared plus the 2 pi r squared. Okay, so let's see if we can do a little bit of cleanup here. For that first term, the 2 pi r would just multiply with the numerator to give us 200 pi r over pi r squared. And then what's going to happen is that the pi's are going to cancel, and one of the r's is also going to cancel. So let's call that 200 over r. So 200 over r plus 2 pi r squared. So now that's a function of a single variable. It only involves r, and we can think about taking the derivative. So now we're ready for step 3. So we're going to set f prime equal to 0. Okay, well, looking ahead to take the derivative, this first term of f, if you wanted, you could call it 200 r to the negative 1, just to make life a little easier when you take your derivative. So f prime would be minus 200 r to the negative 2. So the power decreases when you take your derivative. And then you'd have plus 4 pi r. Okay, and we want to take this and set it equal to 0. So minus 200 r to the negative 2 plus 4 pi r equals 0. And when you have this situation where your equation just has 2 terms, consider moving one term to each side of the equation. So you'd have 4 pi r equals 200 r to the negative 2. Or let's write this right side as 200 over r squared. Okay, so then we can multiply both sides by r squared, and we could get r cubed over here. So 4 pi r cubed equals 200. Or in other words, r cubed equals 200 over 4 pi. So what we could do here is just cancel a factor of 4 from the top and the bottom and call that 50 over pi. Okay, and that's going to lead us to our answer here. Solving for r, you could take cube roots of both sides, and you could say r is going to be the cube root of 50 over pi. So that whole 50 over pi is under the cube root. So let's scroll back to the question for a second, and we'll just figure out what quantities we need to give in our answer. So the question was asking us to find the dimensions, or what dimensions minimize the surface area. So meaning we need to give both R and H in our answer. Okay, that means we're going to need our formula for H, which we had right about here. We'll use that to find our H value at the end of the problem. So let's just jump to a new page here to finish up. So by the end of step 3, we had found that R was the cube root of 50 over pi. And here's step 4, where we're going to give our answer. So we're going to take this quantity, R equals the cube root of 50 over pi, and we are going to plug it into our formula for H, which was 100 over pi R squared. Okay, so that tells us that H looks like 100 divided by pi times, now we need to square R. Okay, let's think of R as being 50 over pi to the 1/3. It just might make life a little easier when we go to our calculator. So a cube root of something is the same thing as raising something to the 3rd power. And therefore, when we say R squared, we can call that 50 over pi to the 2/3. So then, if you would like to give a decimal answer, that would be fine. The idea is you just don't want to round off until the end of the problem. So you wouldn't want to round R off and then calculate H, because you'd have a double rounding error. You want to keep H exact, and then from here you can round H and you can round R as well. So if you want to try putting these into your calculator, the values come out to about 2.52 centimeters for the radius, and for the height, it's about 5.03 centimeters. And that gives us our answer. So basically, this is the can of soup problem that Campbell's Soup and every other company that makes cylindrical containers has to deal with. They're trying to minimize the amount of packaging that they need to use in order to sell a given volume of product to the consumer. So that is all about maximizing and minimizing functions with restrictions. Thanks for watching.